at the different parts of the formula sheet. So one that actually covers a lot of things is this x to the power of n, which, as I showed you previously, works for all sorts of values of n. But the thing is, there's a lot of things that don't look like that, which are actually like that. So if I have, for example, y equals the square root of x. If you look on your formula sheet, you won't find anywhere there's a square root. But you may remember from algebra that a square root is the same as a half power. So if we try to work out the square root, the derivative of the square root of x, it's actually one of these x to the power of n ones. Even though it doesn't look like it, it is. And when we differentiate that, we get the half comes down the front, and we drop power by 1, so a half minus 1 is negative a half. Okay, so roots, even though they don't look like it, are actually covered by this line on the formula sheet. Also things like y equals 1 over x cubed. Again, on the formula sheet, there's not an obvious 1 over thing, but hopefully you remember from algebra that a 1 over is the same as a negative power. So 1 over x cubed is the same as x to the power of negative 3, which means that if we differentiate it, we get the power comes down the front, and we reduce it by 1, and we end up with this. And we can do combinations of those things. So we can have things like y equals 2 over the cube root of x to the power of 4 minus x cubed plus 3x to the power of 7 minus x to the square root of x cubed. That'll do. That's ugly enough. If you can do that, you can do any of the things you have to be able to do here. Okay, so all we need to do is, first of all, we need to write it in forms that just look like a bunch of these. So that 2 just looks after itself. This is x to the power of negative, because it's on the bottom line, power of 4 and third root. So power negative 4 over 3 minus x cubed plus 3 lots of x to the power of 7 minus x to the power of 3 over 2 as the actual function. So I haven't differentiated at this stage. I've just rewritten the function. So it's still y. It's not y dash. It's not dy by dx. I have not differentiated. I haven't gone anywhere. Okay? It's like trying to drive my car to Christchurch. All I've done is put petrol in the car. I've got ready to go. I haven't actually driven anywhere. I've just got it ready to go. So now it's ready to go because these things all look like this thing up here. So I just go through and now I can actually do the derivative. So dy by dx equals, bring the number down the front. The 2, don't worry about the 2, just multiply it. So negative 4 thirds times 2 is negative 8 thirds. So it's still 2 lots of this now. X to the power of negative 4 thirds minus 1 is negative 7 thirds minus number down, power down the front, reduce it by 1, plus 3 lots of 7, 21, x to the power of 7, minus, bring the number down the front, 3 over 2 x to the power of 1/2, taking 1 away from the power. Okay, so even though when you look at it, it looks really ugly and it looks like it doesn't really fit this picture, it's actually just one of those that goes like that. There's one other case that sort of is this type, but it's actually got its own line on the formula sheet, and this is if we just have a constant. So if y equals 3, and we want to differentiate that, the formula sheet tells us, if you look on the formula sheet, it's got a constant turns into 0. So when we differentiate a constant, we always get 0. So the answer to this one is dy by dx equals 0. And there's a couple of ways of thinking of that. One is, this is exactly the same as y equals 3x to the power of 0. Remember, x to the power of 0 is equal to 1. Anything to the power of 0 is 1. This is just 3 times 1. Gets you back to 3. And clearly, when I differentiate that, bring the 0 down, 3 times 0 is 0. And who cares what else there is, because 0 times anything is still 0. The other way you could think about it, you could go, ooh, let's just draw a graph. That's my graph, that's the x-axis, that's the y-axis. The graph of y equals 3 just looks like that. Everywhere y is equal to 3, just a straight line going across. What's the slope of that graph? Well, let's try this point. The slope at that point is 0. Let's try this point. Oh, look, the slope there is 0 as well. What about this point? Oh, another one. That's 0 as well. It doesn't matter where I choose it, the slope's equal to 0. So if my graph is just a straight line, then the slope is equal to 0 at any point. Yeah? So when I'm doing a derivative, whenever I've got a constant, it differentiates to 0, which means that if I have things like y equals 3x squared plus 4x minus 2, and I want to differentiate that, 2 3s are 6, drop the power by 1, which will give me a 1, which I'm going to ignore. This is effectively 4 to the power of 1, so bring the 1 down the front, 4 times 1, x to the power of 0, which is just 1, so I'm going to leave that off, and that's just a constant, so when I differentiate it, it goes to 0. Okay, so those are the things that you need to just be familiar with and start working on. So when you've got a squared, you're going to end up with a power of 1, which you don't write. If you've got a power of 1, which you haven't written, you're going to end up with a power of 0, which goes away. If you start with a constant, you're going to end up with nothing left. Okay, so this is the derivative of that function. And those are the various combinations that work with those two things on your formula sheet.